When working with linear and absolute value equations, our main strategy involved using inverse operations to isolate the variable. But then, when we worked on solving quadratic equations using the factored form, most of our discussion centered around the zero product property. This shift in strategy was due to a key difference about the factored form. The variable showed up twice instead of a single time. When a variable shows up multiple times in an equation that can't be easily simplified, then isolating the variable doesn't work because there would be multiple variables to isolate. This is the main challenge that we face when solving quadratic equations, because most quadratic polynomials contain a linear term in addition to the quadratic term, which means that the variable shows up multiple times. Thankfully, there's a workaround. All quadratic polynomials can be converted into the vertex form, and one of the key features of the vertex form is that the variable only shows up once. This single instance of the variable means that quadratic equations involving the vertex form can be solved using inverse operations to isolate the variable. So let's go ahead and get some more practice with that skill. Let's start things off with this example, where the vertex form is equal to 0. And as we just mentioned, we'll use inverse operations here to isolate the variable. In our first couple of examples, we'll do some boxing to emphasize which portions of our equation function as distinct units, so that we can more easily identify which operation to undo. Thus, in this problem, we'll draw a box around the parentheses and the square, since that's a distinct unit within the equation. Then, we can see that we need to add 49 to both sides, meaning that the box is equal to 49. Next, we'll replace the box with the expression it represents, at which point we're ready to draw another box. This time, let's just draw a box around the expression inside the parentheses. This shows us that the box is being squared, which we can undo by taking the square root and splitting the equation into two new equations, one with a positive square root and one with a negative square root. Once we do that and replace our boxes with their corresponding expressions, we can see that we just need to subtract 4 from both sides of both equations to get our final answers. And since this is our first attempt at solving an equation containing the full vertex form, let's check our answers to make sure that they're correct. Then, once we see that they are correct, we're ready to move on to the next problem. In this problem, notice that our vertex form is equal to 20 rather than 0. You might think that this would be a problem based on our experience with equations involving the factored form, but it turns out to not really matter for the vertex form. Since our first step when isolating the variable is to eliminate the constant from the vertex form, we're going to end up with a constant on the right side anyways, so having a constant there to start with doesn't matter much. From here, we can box the expression inside the parentheses, take the square root, split our equation into two parts, and finish solving to see that v is equal to 11 or 5. Next, let's try solving a couple equations without boxing. In this case, we can add 27 to both sides to see that the square of the parentheses is equal to 25. This means that the expression inside the parentheses could be 5 or negative 5, which we represented visually by taking the square root of both sides of the equation. Finally, we can add 2 to both sides of both equations to see that m can be either 7 or negative 3. Our next equation will follow a similar process, but when we get to the point of taking the square root, notice that the square root of our constant on the right side won't simplify to an integer. In fact, since 67 is a prime number, the square root won't simplify at all. Thus, when we split our equation into two parts, we'll just say that n plus 12 can be equal to the square root of 67 or the negative square root of 67. From there, we can finish solving each equation like this, and since rational numbers don't generally mix well with irrational numbers, there's no way to further simplify our answers. Sure, we could use a calculator to approximate each of these values, but if we want to show the exact answers, this is about the best we can do. There are, however, a couple other ways that you might see this answer written. A common convention when writing expressions that contain a square root is to keep the square root at the end of the expression. What this means for our answer is that instead of subtracting 12 after the square root, we could start our expressions with a negative 12 and then either add or subtract the square root. This may not seem like a big change, but it can help avoid some confusion, especially when writing by hand. Another method of writing this answer takes advantage of the fact that our two solutions look almost identical. They both start with a negative 12 and both end with a square root of 67. The only difference is whether we're adding or subtracting that square root. Because of this, our answers are sometimes written this way. This new symbol is read as plus or minus, and so the whole answer can be read as n is equal to negative 12 plus or minus the square root of 67. The meaning of this symbol is that it can be interpreted, unsurprisingly, as either a plus sign or as a minus sign. If we treat it as a plus sign, that would correspond with this answer that we had previously. But if we treat it as a minus sign, that would correspond with this other answer that we had previously. Therefore, we were able to represent our two solutions with a single expression. And while this doesn't change the fact that we still have two solutions, this new way of writing our solutions is often more convenient and compact. With that, let's look at a few more equations involving the vertex form. In this equation, we'll start by adding 1 to both sides, and then we'll take the square root. In fact, now that we've introduced the plus or minus sign, we can represent this step a bit more precisely by placing a plus or minus sign in front of one of our square roots. Next, we'll simplify the square root of 48 by identifying that 16 is the largest square number that goes into 48. Then, while we would normally split our equation into two new equations at this point, let's just stick with the plus or minus notation. From there, we need to add 3 to both sides of the equation. But since we want to avoid having anything after the square root if possible, we'll put the 3 at the beginning of the right side expression. That gives us this equation, which succinctly represents both of our solutions. Our next problem contains an aspect of the vertex form that we've avoided up to this point. Notice that there's a constant in front of the parentheses, which represents the a value in the official vertex form. So far, we've only looked at situations where a is 1, but it's time to venture outside of that box. We can still start, as usual, by adding 18 to both sides. But at this point, we do need to think a bit more carefully about the operation that we should undo next. In fact, this might be a good place to draw a quick box to help us out. The main question to ask ourselves here is one we've asked several times before. What is the exponent attached to? The answer is that it's attached to the parentheses, so the only thing being squared is the expression inside the parentheses. This means that we can draw a box like this to indicate this unit of the expression. Then it becomes clear that the outermost operation is multiplication by 2, so we can divide both sides by 2 to move forward. After this, we can proceed as normal, and when we subtract 5 from both sides, we get a final answer of negative 5 plus or minus 7. There is something different about this answer, though, compared to previous times that we've used the plus or minus sign. Since negative 5 and 7 can be easily combined with addition or subtraction, we would really prefer that our answer reflects that. Thus, in this case, it's more common to split things into two equations and write our answers this way. For our final two problems, let's check out some equations that have fractions in them. For this first equation, we need to do a couple fraction operations to get to the point of taking the square root. Once we get to that point, though, the square root itself works out rather nicely. Because of this, we'll split the equation into two parts right away, and when we add 2/5 in both equations, we get these two answers. The next equation doesn't work out as nicely, but when we get to the point of taking the square root, we are still able to simplify that square root a fair amount. Then, we subtract 4/3 from both sides to get this answer. You may even notice here that since both terms on the right side of the equation have the same denominator, we can combine them into a single fraction like this. Interestingly enough, it's hard to say which of these answers is more simplified, but in this video series, we'll generally prefer the second option. Now, as we've seen many times already, there are plenty of other forms that quadratic expressions can take. And thankfully, we can still use our vertex form strategy in those situations. In previous videos, we've already seen that we can convert any quadratic expression into the vertex form through a relatively consistent set of steps. And now that we know how to solve equations involving the vertex form, we can combine those strategies to solve any quadratic equation. Let's put that into practice with these equations. In our first example, we have an equation where the left side is in the standard form and the right side is simply 0. So let's convert the left side into the vertex form by making an informed guess at which perfect square it involves, and then adjusting that perfect square by a constant. From there, we can rewrite the equation by setting our newly found vertex form equal to 0, and then we're ready to solve. We end up getting solutions of 2 and 10, and just for good measure, we'll plug those solutions into our original equation to verify that they are correct. From there, we're ready for our next problem. The main difference with this problem is that the quadratic expression is not equal to 0. As we've already discussed, though, this isn't a big deal for the vertex form, as long as the non-quadratic side of the equation is just a constant. In the end, we get this expression as our vertex form, and after that, the solution process leads us to these solutions. Now, while this was a completely acceptable way to get our solution, there is another strategy that we could try. One of the more cumbersome aspects of converting to the vertex form is identifying the constant outside the perfect square. But then we immediately move that constant to the other side of the equation. So what if we just moved our constant to the other side earlier? Here's what that would look like in this case. Notice now that we have a much simpler looking quadratic expression on the left side, and that expression will allow us to convert to a perfect square more easily. From there, we know from the linear term on the left side that our perfect square is going to be y plus 2 squared. But that perfect square also contains a constant of 4. This means that if we add 4 to both sides of the equation as our next step, then converting the left side to the vertex form will be super simple since it's just a perfect square. Then, we can jump straight into taking the square root and work forward from there. This process, involving manipulating one side of the equation into a perfect square rather than formally converting into the vertex form, gets us the same solutions as our first strategy. And since this process avoids the finer details of the vertex form, this will be our preferred strategy moving forward. Let's practice that strategy again with this equation. Notice this time, though, that both sides have at least one term with a variable. We can handle that issue easily by subtracting 5a from both sides to get this equation. Then, Let's add 10 to both sides so that all the constants are on the non-quadratic side of the equation. From there, we can add 9 to both sides of the equation since that gives us a perfect square on the right side. Next, we can take the square root of both sides, which will also involve simplifying the square root of 12. But once we do that, we can finish things off by adding 3 to both sides. For our next problem, let's consider a quadratic expression that has a leading coefficient other than 1. We'll once again start by moving our constants to the non-quadratic side, but then we can see that the leading coefficient makes things a bit more complicated than what we've dealt with up to this point. One approach to take from here is to factor out a 5 on the left side expression, which will help us identify the perfect square to use and the constant to add to both sides. And this strategy will eventually lead us to this answer. However, when it comes to solving equations, we have yet another sneaky tool that we can use to help simplify things. The most annoying part of the equation here is the coefficient of the quadratic term. So why don't we just divide both sides of the equation by that coefficient? Sure, we end up working with a lot of the same numbers that we had before, but at least the process of identifying our perfect square doesn't involve a leading coefficient anymore. Eventually, we get to a point where our calculations look identical to what we did in our first approach, but this division by the leading coefficient allows us to trim down the complexity of the problem. In the end, solving quadratic equations using the vertex form is in many ways easier than converting quadratic expressions into the vertex form. We start by distributing to get rid of any parentheses, and then we move all the terms with variables to one side of the equation, with the constants being moved to the other side. Then, we can divide by the quadratic coefficient, or multiply by its reciprocal if that's easier, to avoid dealing with a leading coefficient when we convert to the vertex form. Next, we add a constant to both sides so that the quadratic side of the equation is a perfect square. And finally, we take the square root of both sides and solve from there. This sequence of steps allows us to solve any quadratic equation that we might encounter, which makes this strategy flexible and effective. That concludes part 2 of this video on solving quadratic equations using the vertex form. Hope you learned something new, and thanks for watching.